Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we're doing a deep dive into, well, pretty much the whole engineering life cycle. We're looking at everything. I mean, from the really abstract, like theoretical performance modeling, the stuff done on supercomputers, all the way down to the nitty-gritty specs for fitting parts together, pins, bushings, bolts, the works. Yeah, the idea is to give you a kind of comprehensive shortcut. How are top-tier components really designed and built efficiently?
And if you boil it all down, I think the core theme that emerged from everything we looked at is just seamless efficiency. Every single decision, whether you're talking about maximizing strength or, getting motion down to the Angstrom level, it's all driven by getting the most performance out of the least resources, constantly pushing for maximum output from minimum input.
Okay, let's start unpacking that and maybe start at the most abstract end, topology optimization. For listeners who maybe haven't used the software, what's this wizardry actually trying to do?
Right. Topology optimization is basically that efficiency theme taken to its extreme. You're trying to maximize a part's structural performance, stiffness, load capacity, whatever, while using the absolute minimum amount of material. And this isn't just academic. Less material means, well, direct cost savings in manufacturing, obviously, but also a lighter environmental footprint. Big savings there.
It sounds amazing, but the shapes that come out of it, they often look really organic, almost alien, like a complex honeycomb or something. They don't look like something you'd design traditionally.
Yeah.
How do engineers actually arrive at those shapes without just making, a million physical prototypes?
Yeah, you definitely wouldn't want to do it that way.
Yeah.
It relies heavily on advanced computation. Our sources point to optimization techniques like genetic algorithms, particle swarm optimization,
Yeah.
things like that. These algorithms essentially run millions of simulated design variations inside the computer to kind of evolve the best shape for the job. The huge benefit is skipping all that costly, time-consuming physical trial and error that, traditional design often got bogged down in. Really speeds up the concept stage.
But I wonder, does that super complex, optimized shape, while it's great for material use, make it incredibly hard or expensive to actually make the part? Using traditional machining, for instance, seems like a potential trade-off.
Oh, it absolutely can be. That's a really important point. And it's why topology optimization is so often paired with additive manufacturing, 3D printing. But you hit on something crucial there, which leads us to maybe the biggest hurdle for wider adoption right now. Standardization. See, different fields, aerospace, medical, automotive, they have wildly different needs. Think extreme temperatures in space versus like high-volume consumer goods. And because those requirements and the material properties involved, yield strengths, densities, fatigue life, are so varied, there's just no single uniform set of optimization rules that works everywhere. That lack of common protocols is really what holds back broader, more consistent use across all industries.
That makes total sense. Okay, let's shift gears then. From optimizing static structures to getting really precise, really reliable motion. This brings us to flexures. When you need super smooth, fine movement, why do flexures often win out over, say, traditional bearings?
Well, the big advantage with flexures is that inherent smoothness you mentioned, and also their linear elastic operation. Unlike bearings, there's no rolling or sliding friction, right? The movement comes purely from the material bending elastically, and that high linearity is just absolutely vital for achieving the kind of extreme repeatability needed in things like semiconductor lithography or nanotech manufacturing.
Right, and when we start talking formally about how mechanisms move, we kind of leave intuition at the door and get into the math of constraints. I always need a refresher on the rule that governs these kinematic systems. Can you walk us through the basics again?
Sure, we use kinematics to really quantify and control motion precisely. And the common approach relies on Blanding's rule of complementary patterns. It's kind of the fundamental equation for designing constrained motion. The key idea is this relationship. The residual freedom, let's call it R, has to equal 6 minus the number of constraints applied, C. So R equals 6 minus C.
Equals 6 minus C. Got it.
Yeah. So if you want something to move only in one specific direction, like a piston in a cylinder, you need to apply exactly 5 constraints. That leaves it with just 1 degree of freedom, R equals 1.
Yeah.
This mathematical approach ensures you get only the motion you want and nothing else. No wobble, no unwanted shifts.
Okay, and the sources mentioned Angstrom-level repeatability. That's an incredibly tiny scale, almost hard to imagine. What sort of perfect storm of conditions needs to happen for these bending components, these flexures, to perform that precisely without failing?
Yeah, Angstrom level is amazing. To get there, You basically have to eliminate almost all energy loss and any potential material degradation. So first, the material needs incredibly low hysteresis. That means it springs back perfectly after bending, without losing energy internally as heat.
Okay, low hysteresis.
Second, you absolutely cannot have any dislocation motion within the material's crystal structure. So the stress you apply, sigma, has to be way, way below the material's yield stress, sigma yield.
Much less than yield. Makes sense.
And finally, how you assemble it is critical. There can be zero microslip or friction in any mounting points or joints. And the parts themselves can't yield even a tiny bit during assembly. It all has to stay purely elastic.
Wow, okay. So when you're picking the material for that kind of demanding job, it sounds like you need to look beyond just the basic strength number, the yield strength. Why the focus on these normalized property ratios?
That's a great question. For flexures, what we really care about is the maximum elastic strain energy the material can store before it deforms permanently. And the ratio that captures this potential is the yield stress divided by the Young's modulus, so sigma y over E.
Sigma y over E, okay.
Yeah, that ratio tells you how much a material can bend elastically relative to how stiff it is. So for example, titanium V comes out really well with a ratio around 1.00, whereas something like aluminum 7075 is quite a bit lower, maybe 0.70. Using these normalized ratios helps designers push the performance, like the range of motion or stroke, while balancing other factors like density or cost.
All right, let's move down to maybe the most fundamental way we join things. The bolted joint. This seems like a classic sticking point for engineers starting out. When you preload a bolt, clamp parts together, how should we think about the stiffness? Are the flange and the bolt acting in parallel or in series?
Ah yes, the bolted joint puzzle. During the initial preloading, they act in a series relationship. That's the crucial part to remember. Think about springs. In series, they both see the exact same force, which is the preload tension. But because they have different stiffnesses, the bolt stretches a certain amount and the flange compresses a different amount.
Ah, okay. Same force, different deformation series.
Exactly. If you incorrectly model them as parallel, your calculation for the overall stiffness of the joint will be completely off.
Right. Okay, now, what if that preloaded joint also has to resist shear forces? Forces trying to slide the two parts sideways against each other. The gut feeling might be that the bolt shank itself is taking that sideways load. Why is that often wrong?
That's a really critical piece of engineering understanding. In a properly preloaded joint under shear, it's overwhelmingly the friction between the clamped surfaces that resists the load. That friction is generated by the huge clamping force from the preload. So the coefficient of friction in getting that preload right are absolutely paramount.
So the bolt isn't really acting like a pin in shear.
Not primarily, no. If you need direct shear resistance, maybe because of high vibration or impact loads where friction might be overcome, then you have to add features specifically for that, like dowel pins or shoulder bolts. They are designed to take shear load directly in bearing.
Got it. And kind of underpinning all this assembly work is the actual language of manufacturing, the tolerance standards. We have to specify dimensions with total clarity.
Absolutely. Precise communication is key. Manufacturing runs on detailed specs. It covers everything, from the different classes of screw threads, like unified threads here in the US or metric threads elsewhere, all the way to classifying how parts physically fit together. It's the difference between something that rattles loose and something that's basically a permanent bond.
And those fits have specific names.
They do. We generally talk about three main types. Clearance fits, where there's always a design gap between the parts. Transition fits, where depending on the actual tolerances, you might get a small clearance or a small interference. And then the critical ones are interference fits. These are things like force or shrink fits, often designated FN1, FN2, FN3, and so on.
FN1, FN2.
Yeah, those parts are intentionally made so one is slightly larger than the hole it goes into. You have to force them together, maybe by heating one or cooling the other. The FN number indicates how much interference, how tight that fit is. Creates a very strong, solid joint.
Okay, bring it back to the preload for a second. We need to actually measure that tension to make sure we get the clamping force, the friction we need. The sources mentioned three main ways to do it, but only one is really easy in practice. What's the trade-off?
Right, you got three options. Method 1, directly measure how much the bolt stretches. Very accurate, but usually impractical in the field. Method 2, use bolts with embedded strain sensors. Also very accurate, but expensive.
Okay.
Method 3, measure the applied torque needed to tighten the bolt. This is by far the easiest and fastest method, which is why it's so common.
Well, it's not perfect.
Not for ultra repeatability, no. The big drawback with torque is that a huge chunk of the effort you measure, maybe 80 or 90%,
Hmm.
isn't actually creating tension, it's just overcoming friction.
Friction in the threads and under the bolt head.
Exactly. And that friction can vary wildly depending on the lubrication,
Yeah.
surface finish, cleanliness, even temperature. So using torque is fast and convenient, but you sacrifice precise control over the actual tension achieved.
Okay, let's switch from static joints now to dynamic systems. Belt drives are everywhere. When you're trying to optimize these for efficiency, noise seems like a really big deal. Are some types of synchronous belts just inherently quieter?
Oh, definitely. As a general rule, synchronous belts, the ones with teeth, tend to be noisier than, say, V-belts just because of that meshing action. But yeah, there are big differences. Advanced designs, like the Power Grip UT3 drives mentioned in the sources, are specifically engineered to be much quieter than older synchronous designs. They have improved tooth profiles and meshing characteristics that really reduce that impact noise as the teeth engage the sprocket.
And if there's one guaranteed way to make any drive system noisy and fail prematurely, it's misalignment, right? What's the kind of critical tolerance limit engineers need to stick to there?
Misalignment is the absolute enemy. Whether it's angular, the shafts aren't parallel, or parallel offset, the sprockets aren't lined up, it causes terrible noise, uneven wear, high temperatures, belt tracking issues. It's just bad news.
Well, what's the magic number?
The rule of thumb we found is pretty tight. Misalignment shouldn't exceed about 1/4 of a degree angularly. Or if you think about it linearly, that's roughly 1/16 of an inch offset for every foot of distance between the shafts.
Wow, that's not much room for error.
No, it isn't. If you go beyond that, the belt will try to climb the flange of the sprocket, generating heat and noise and wearing out very quickly.
Okay, shifting over to chains now. They often play that dual role, right? Power transmission, but also just conveying things. What are the key wear limits we look for when deciding it's time to replace a chain?
Yeah, chain manufacturers are usually quite specific about this. It's based on wear elongation, basically, how much the chain has stretched because the pins and bushings have worn down. For chains used in high-speed power transmission, the typical replacement point is when that wear elongation hits 1.5% of the original length.
1.5%. Okay.
For conveyor chains, which usually see lower speeds and stresses, the limit is often a bit looser, maybe around 2% elongation. Exceeding those limits risks chain jumping or breakage.
We also saw some really interesting examples of specialized chains, particularly ones designed to run without any lubrication.
Yes, the LAM-BDA roller chains were a fascinating example of material science in action. They use bushings made from sintered metal that's impregnated with oil, and the pins often have special coatings. This design lets them run without external lubrication, and at lower speeds, they can apparently outlast standard chains needing lube by maybe up to 30 times. Huge maintenance saver, especially in hard-to-reach spots.
That's impressive. And linking back to noise again, why is it that larger pitch chain systems tend to be noisier than smaller pitch ones?
Our sources confirm this generally comes down to something called chordal action.
Chordal action.
Yet, picture the chain links engaging with the sprocket teeth. Because the sprocket is a polygon, not a perfect circle, the chain path actually rises and falls slightly as each link engages and disengages. That up and down oscillation is chordal action. With larger pitch chains, the links are longer, the sprocket flats are longer, and this chordal rise and fall is just more pronounced. It creates more vibration and therefore more noise. It also tends to accelerate pin and bushing wear, which adds to the noise too.
Okay, wow. We've covered a ton of ground here. We went from, abstract computer optimization of shapes all the way down to the friction in a single bolt thread. When you step back and look at all of it, what's the big takeaway for the design junkie listening right now?
I think the biggest takeaway is that truly successful high-performance mechanical engineering demands this absolutely seamless integration of everything. You have to think about the optimal shape the topology algorithm gives you and ensure your flexure hits that Angstrom-level repeatability using materials with just the right sigma Y/E ratio, and still manage to get the preload and friction exactly right on every single fastener, holding the whole thing together. It's all connected. High performance isn't magic. It relies entirely on rigorously applying precise standards and understanding the details, the bore tolerance on a pulley, the groove profile on a sprocket, the class of fit for a pin. Everything matters.
And that leads perfectly into a final thought. Because it's easy to stop at the spec sheet, right? The supplier tells you what the part does. But let's think about the manufacturing process itself for a second. Consider corrosion-resistant chains, maybe ones that get chemically plated for protection. Plating sounds great, adds resistance. But that plating process often involves high temperatures.
Right. And that heat exposure can actually change the physical parts in subtle ways. If those chains, for instance, are plated after they're assembled, that heat can cause the press-fit components, the pins forced into the side plates, the bushings pressed into the links to actually lose some of that critical interference fit they were designed with. The heat allows things to relax a tiny bit.
So here's the trade-off to ponder. How does a process designed to add a benefit, like corrosion resistance via plating, potentially reduce the fundamental strength characteristic that interference fit, which in turn might lower the chain's maximum load capacity or even shorten its wear life compared to an unplated, properly assembled chain? It forces you, the designer, to look beyond just the final spec and consider the entire manufacturing life cycle and its potential hidden impacts. That's your deep dive homework for this week.
Definitely some food for thought there. Until next time.